Before the complex spectral theorem, we need one missing bridge, Schur triangularization. The idea is simple. Take the old triangular basis and force it to behave orthonormally. Yes, we are making basis vectors learn manners. Back when we proved Cayley-Hamilton, we used the ordinary complex upper triangularization theorem. The important phrase is some basis. Not necessarily orthonormal. Mathematics loves hiding the inconvenient adjective. So there is a basis V1 through Vn, and the matrix of T is upper triangular. We now translate upper triangularity into the language that Gram-Schmidt can preserve. If the matrix is upper triangular, then each initial span is T invariant. For example, T applied to Vk only uses V1 through Vk, never the later basis vectors. That invariant flag is the real object we need. The matrix is just the spreadsheet version. Because apparently even linear algebra needed paperwork. We also already proved Gram-Schmidt. From a linearly independent list, it creates an orthonormal list. Starting from V1 through Vn, Gram-Schmidt gives E1 through En. The key is that Gram-Schmidt preserves every initial span. It does not scramble the flag. It just cleans it. Schur triangularization says, over the complex numbers, the triangularizing basis can be chosen orthonormal. Same triangular shape, better basis. A suspiciously useful upgrade, which means it deserves a proof. Start with the ordinary triangularization theorem. It gives some basis, not yet orthonormal. Call that basis V1 through Vn. For each k, define V sub k as the span of the first k basis vectors. Because the matrix is upper triangular, every V sub k is invariant under T. This invariant chain is called a flag. Naturally, linear algebra needed medieval vocabulary too. Now apply Gram-Schmidt to the triangularizing basis. We get an orthonormal basis E1 through En. Gram-Schmidt preserves initial spans. So the first ke vectors span the same space as the first kv vectors. Therefore those initial spans are still T invariant. This is the whole trick. And somehow it is allowed. Now we translate the invariant spans back into matrix entries. Since Ek belongs to the number k-span, Tek also belongs to the number k-span. So Tek is a linear combination only of E1 through Ek. There are no later basis vectors. No Ek plus 1, no En, no surprise guests. In the orthonormal basis E1 through En, the number k column has zeros below row k. That is exactly upper triangular. So the ordinary triangularization basis can be replaced by an orthonormal triangularization basis. The basis got cleaned. The triangular structure survived. Next time, Schur triangularization becomes the engine of the complex spectral theorem. The plan is normal operator, Schur triangular matrix. Then normality forces the triangular matrix to be diagonal. And diagonal in an orthonormal basis means an orthonormal eigenbasis. That is the complex spectral theorem. Finally arriving like it paid tuition.